brand new units. This is a two-part unit. This is Unit 3, Polynomials and Sinusoidal Functions. So our first section is polynomials. So we're going to discuss the different 4 types of polynomials that we are going to discuss. So what is our outcome we're going to be discussing today? Describe orally and written the characteristics of polynomials by analyzing graphs. So again, we're going to analyze graphs, we're going to analyze equations as well. So there's certain things we can find out from our equations. So if we first of all look at set A. Set A is different from set B. What do you notice the difference is between set A and set B? What do you notice the differences between those guys?
Set A is positive and set B is negative.
Perfect. Set A is positive, set B is negative. There's one more difference. What does set B have that A does not? Set B has coefficients other than a positive 1. If you look at set A, almost all of them are positive 1 except for our constant y equals 2. So in front of every single one of these, first thing we notice is that each of these has a hidden positive 1 in front. Okay? So these all, okay, are going to be positive functions. We're looking at B, they are all negative functions. We're going to deal with set C and D in a moment. So if I'm going to be drawing a linear function, what do you notice the difference between the first two are? Constant and linear functions. What are you noticing? It should be very obvious. Look at the equation. What is different between this equation and this equation? We look at both of these equations. How are they different? Yep.
Linear has x variable.
That's right. So for linears, we have a variable. Over here on constants, there's no x at all. So we call those guys the constantly lonely ones. These guys have no variable. Okay? So because they have no variable, they are a horizontal graph only. And because it is a horizontal graph, it will have no x-intercepts. It will have no x-intercepts. Every polynomial graph will have a 1 y-intercept. Every graph we see this year is going to have a y-intercept. Only one. But not every graph has an x-intercept. Right now we're noticing constant linear graphs are not going to have an x-intercept unless it is this graph. What am I writing right now? Y equals 0. What do we know that is? It's got another name. Y equals 0. It's a line on your graph. It's the x-axis. So because this is the x-axis, if we have a y equals 0 line, we will have an infinite number of x-intercepts because it's going to touch on every point on that line. Okay? So constant functions are always horizontal lines, either above the x-axis or below the x-axis. We never talk about the one y equals 0 because that is the x-axis. Okay, that's in terms of constants. So if I was going to graph this first constant, I have a positive 2. I would put a dot on positive 2, and I would draw an arrow pointing left and right. Okay, so that is my constant set A. We're going to do set A all in blue, and then we will do set B all in red. So now I'm going to do set B. I'm going to draw y equals negative 2. So y equals negative 2 is going to be down on the bottom at negative 2, and it's going to go left and right. Okay? So that is a linear constant graph. Yes, they're still called linears, but they're constant. Okay? Constant meaning no variable. The minute I want to take that slope from 0, and I want to add a different slope, that means I've got an x variable. So, we notice there's nothing on the end of these linear equations. Well, that's like saying plus 0. So that means that all those linear equations are all going to cross through our origin. Okay? So these guys are like saying plus 0, plus 0, plus 0. Okay? So, the linear functions, so far we've got both the constant functions We've got our blue one we have graphed, and we have our red one we've graphed. Now we're on this same linear one. We are going to graph our two linears. Y equals x plus 0. Well, the plus 0 is just telling us he goes through that origin. So the slope is telling me it's going to go one up, one right, one up, one right, one up, one right, or one right, one up. So our graph, being set A, is going to go through our middle. Okay? There is our y equals x. Now the next one, if I go to my red one, I'm going to now do y equals negative 3x. If we were to graph that one, again, it's going to go through the origin, but this time, my slope is telling me we always put our slope over 1. So anything with the x variable is always over 1. So right now, that's negative 3x over 1. The bottom number is telling us we're going to go to the right. The top number tells us up or down. So right now, this one's going to go 1 right, 3 up, or sorry, down. 1 right, 3 down, 1 right, 3 down, because it's negative 3. So I would make my dot 1 right, and then I go 3 down, make a dot. 1 right, 3 down, make a dot. 1 right, 3 down, make a dot. Then I'm going to join, well, it's much steeper. It's going to join those points. Okay? So this red graph here is our y equals negative 3x. So if we're comparing the blue one to the red one is much steeper. And again, the reason this guy here is much steeper is because he's got that 3 in front. Okay? Remember, those numbers in front of x, those are going to tell us what it does with our graph. So this guy was going 1 right, 3 down. Now we're going to take a look at the next equation, set C. I'm going to raise it for us. Yes?
For that 1 right, 3 down, where do you start?
You always start on the y-intercept. So here I started on the x-axis. So I went 1 right, 3 down, made a dot, 1 right, 3 down, 1 right, 3 down, and then you'd work backwards this way. 1 left, 3 up, 1 left, 3 up, 1 left, 3 up, kind of thing. Okay? All right, I'm just going to clear it, and we're going to go, I'm going to move it up for you so it looks a lot neater. Okay, let's move this guy up a bit. Okay, so now we've got our linear functions. We have this basic linear function doing this. Our y equals x from set A, which is our blue. Then we have our red one, which was doing this. Okay, really, really steep. Now we're going to put this next one on. It's going to be in green. We have an x plus 1. Well, this x plus 1 now gives us our y-intercept. Okay? Those digits without the variable are the y-intercepts always. So now we're going to draw that on our same linear graph. But this time we start at positive 1. So this time I'm starting at positive 1 right there. And now my slope is in front of x. That just means whatever's in front of x, this guy's got a hidden 1. And we put it over 1 always. Okay? The bottom number always moves right. So you're going to go 1 right, 1 up. 1 right, 1 up. You're going to go 1 right, 1 up, make a dot. 1 right, 1 up, make a dot. Okay? We're going to make a dot doing that. Okay? So this, guys, is... Okay, hang on. I need to redraw my graph here for you. So it's going to have the exact same slope. It's going to go through positive 1. Whereas the other blue one, it went through 0. So it's going to be side by side. They just have different y-intercepts. Okay? So these guys are identical. How could I move the green one to sit on top of the blue one? I would just remove the y-intercept. I would make its y-intercept be equal to 1. Or sorry, be equal to 0. And it would start at the same spot. Then you would slide down and cover the blue line. Okay? Now we're going to take a look at our quadratics. For quadratics, we have 3 different types of quadratics. Okay? We're going to deal with set A, our basic one, in blue. So we're dealing with y equals x squared. If I deal with y equals x squared, that's like saying plus 0. I have no x-intercepts except for 0. Same as my y. So here is our y equals x squared. And now I'm going to go to my red. Now my red is saying y equals negative 2x squared. If we remember what a positive and a negative do, what's that negative sign going to make this graph do? It's going to flip upside down. It's like a reflection on the x-axis. So we're going to reflect this guy on the x-axis, and then the 2 itself is telling us it's either wide or narrow. Now, if the digit is between 0 and 1, it's going to be wide. So we call this our a value. So the a value is in front of x squared. Okay, the a value is in front of x squared. Now, if a is greater than 1, I don't care whether it's positive or negative. Negative just means it's going to go down. I'm talking about the digit itself. If it is greater than 1, so 1.2, 1.01, 1.0001, okay, 95, doesn't matter. Whatever the digit is, it's going to create a narrow graph. If a is between 0 and 1, okay, this means between, it's supposed to be an arrow, let's fix that real quick. So like this, if it's written this way, this just means that it's between. That's these arrows that point left, they mean between. So a is between 0 and 1. Well, if that's happening, that's going to give us a wider graph. Okay? So those are two things we have to remember from last year. So we look at our graph, or our equation, and we have a negative 2. Our 2 is greater than 1. Okay, 2 is greater than 1. Therefore, we are going to have a narrow graph. So, if I were to draw a graph, it would be identical to this guy, but it would be inside him. But remember, he's pointing down. He flipped down. So now I'm going to have to take this one that I was drawing and flip him underneath. Okay, and he's going to be narrow. By narrow, what it means is they pull towards the y-axis, the tails do. If they're pointing up, they're going to pull towards. If they're pointing down, they're going to pull towards y. Okay, that's how they make narrow graphs. Okay, so this guy here is our y equals negative 2x squared. You always put the equation after the tail, okay, on the right-hand side. We're not going to put it on the left-hand side with the left tail. We put it at the right tail, okay? So that's how you know which graph is which. Now we're going to go to the green graph. We're going to go to our green graph. I'll let you write this stuff down about the a value so I can erase it here momentarily. So I'll give you a moment to write that down. Okay, we are now going to take a look at our green graph. We're going to draw this graph right here. So we've got x squared minus 3. We have to start at our y-intercept. Okay, our y-intercept in this case is negative 3. So that means I've moved down to negative 3. That's where I'm starting. So down here at negative 3. And again, is it an up graph or down graph? Look in front of x squared. It's up because x squared is positive. So this one's starting down here, and then it's going to go up. Now, do we know if it's wide or narrow? Has the wideness or narrowness changed? No, because there's still just a hidden 1 in front of that x squared. Okay? If there was a different digit, what would the digit 5 make it do? Narrow. Digit 5 would be narrow. What about 0.5? Wider. Okay. All right, let's take a look at the next one. Now we're at negative 2. So we're at negative 2. I'm just going to make this guy in blue. And again, there's a 1 in front of x squared, so it doesn't change how wide or narrow the graph is. So we're just going to plot at negative 2, and he's basically going to cover the other blue graph. Okay? All he did was move down. Now we're going to take a look at our cubic functions. Okay, cubic functions. The thing we're going to notice about a cubic function is the highest exponent on the variable is a 3 first. For quadratics, your highest exponent on your variable is 2. For a linear, highest exponent on your variable is a 1, constant, no variable. Okay? All right, here goes all the writing. Now to cubics. Okay, if we look at our first cubics, I'm going to draw the graphs on this linear just so I can see the equations. But these are going to be the cubic ones. So I'm just going to write cubic so we don't get confused. And this is just so that you guys can see what I'm doing. Okay, so we're going to look at our first x cubed. Well, if we're not sure what x cubed looks like, we're going to first take our calculator out. We're literally going to put in our calculator on y equals. So, do you see a plus or subtract after your x cubed? No, we don't. We only see a hidden 1 there. So if I go to y equals and I go x cubed, okay, so go to your y equals, please, and put in x cubed. Then we're going to hit graph. So, this guy, again, this one's going to be blue, is going to go up through here. Okay? Hopefully your graph's a little better than mine. That's just going to pull down a little bit. Let's see here. Should go through the middle a little bit better. Good. So it's going to have like a little flat spot in there. Okay? That little flat spot is called a point of inflection. And this is where the graph just moves over. It doesn't change directions. So one of the things we're going to notice is that certain graphs change directions and certain graphs do not. So a linear graph goes in one direction, doesn't change direction. If we look at quadratics, they're going to go up, 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 change direction, go back down. Or they're going to start upwards and they're going to end upwards. So they change direction once. So however many basically bumps or hills you see, that is going to be how many times they are what's called their turning points. And that's how many times they change direction. So if we look at this cubic function, it didn't change direction at all. It has a point of inflection. All it did was go up, 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 move over, go up, up, up. It did not change direction. Okay? The other cubic functions we're going to deal with will change directions once we have things added to our x cubed. Okay, once we have extra terms. What do you think the -4 is going to do to our graph? It's going to go down. What else do you think it's going to do? Narrow. Good. So this one is going to be really close to the y, and it's just going to go down. So let's check it on our y equals in our calculator. So now I'm just going to go down to the second one, and I'm going to put in -4 x cubed. And now I'm going to graph both of them. So you can see which one looks like it's closer to the y value, closer to the y-axis. The one that's going down is closer to the y-axis. We knew it would be. It has to be narrower. Okay? Okay. Let's take a look at the next couple. So, we have our two cubics that we have on here. So we've got our up cubic, and then we had our skinny down cubic. These ones did not change directions. The exponent on your x variable, the highest exponent is called your degree. So cubic is a degree 3. Quadratic would be a degree 2. Linear is a degree 1. Constants have no variable, so they're degree 0. You have to have a variable to have a degree. Okay? Now what we're going to do is we're going to figure out this guy right here. What it does is it moves our intercept. Right now our intercepts are right here at 0, 0 in the middle. This is going to move our y-intercept down to -4. So we're going to check and see what the graph looks like in our calculator. So we're going to go to our y equals. And we're going to clear it out and put down in there what we want. So we need x cubed -4. Okay, so x cubed -4. We hit graph. Again, this one still just has a point of inflection. It didn't change direction. All it did was change where the point of inflection met the y-axis. So, recapping, right here for our cubics, our first one, our second one, well, our second one is a lot thinner actually, a lot closer to the y. Then we've got this guy. All he did was move down here, and he's going to be identical to the blue one. Okay? Same shape. If I moved him up, he would cover and copy the blue one identically. Okay? The minute we show more terms, okay, the minute we show more terms in our equation, so we're now going to go to our y equals in our calculator again, and we're going to put in this equation. And we're going to make that one go into our y equals. Because we have an x squared term and an x term, that's going to make it change directions. So, in our calculator, in the y equals, we are now going to enter the equation. So, x cubed plus 4x squared plus x minus 6. So, what is the digit without the variable called? Constant. And he's always our y-intercept. So, where's our y-intercept on this one? Down at -6. Let's see our graph. So, this guy actually changed directions. Okay? So, when we read a graph, we always read it from left to right, the same way we would above. So, on our graph, we're starting down below in quadrant 3. We go up, change directions, go down, change directions again, and then continue going up. This graph is an up graph, okay? And it's got 2 hills or valleys. So because it's got 2 changes of direction, it has multiple x-intercepts. So we're just going to sketch this one on here. So this guy would be sketched through here, and our y-intercept is -6 he would go down to, and then back up. Now, this part of my graph is wrong because he's got to go in through +1. So your x-intercepts, these guys have to touch the proper x-intercepts. Mine don't in this case, but they should touch the proper x-intercepts. Okay? Do you remember how to find x-intercepts on a graph? Let's try it. So, everything is under our second trace menu. Okay, a little hint for ourselves. In order to find x-intercepts, we need to intersect our graph. But in order to intersect it, we need 2 lines or 2 graphs to intersect. You can't just intersect one graph. You have to have 2 graphs in your y equals. So in order to find an x-intercept on this line, on the x-axis, what is y equal to? 0. So, intersect. So into y2, you're going to put 0 always. And that's going to help you find your y and x-intercepts. So let's try this together. I'll let you write that down. Okay, everything will be in our second trace menu. Okay. And now we are going to take a look on here. In your y equals, like I said, in y2, you need to put 0. You have to have 2 equations in here or you can't intersect. Okay? So, we hit graph again. It's not going to show the second line unless you have a colored graphing calculator, because the second line is the x-axis. Now, if we make it thicker, for example, if I go back to my y equals, I can go down, and I can make over here, left of the y equals, I can make this thing twitch. Whoa. I can make this thing twitch, and I can make it go darker. So I'm going to make it a thicker line, so I hit enter once, and now it's a thicker line. So now I'm going to hit graph, and now I can see where it actually intersects on my graph. Okay? So, in order to intersect, you need to have your cursor as close to the dot where you want to intersect as possible. So, for example, we want to intersect right here, and right here. So, 3 different places. So, your cursor is always going to say left boundary. So what you need to do is you're going to use your left arrow right here, and you're going to be making your left cursor anywhere to the left of halfway. So anywhere on the left here, your cursor, and then you're going to hit enter 3 times. After that, you can't just move your cursor. You must hit second trace again. Then you move your cursor. He's got to be over halfway on this side. Then you can find the second one. Then, here's again, halfway from our bottom dip there, we have to be on the right-hand side of it to find the right-hand side one. So I'm just going to show you, I drew it on the graphing calculator here, but I'm going to show you what it looks like now. So, we are going to go second trace, number 5. Now you're going to see my cursor is usually always starting on the y-axis, on the y-intercept. I'm going to hit the left arrow and I'm going to make my cursor move all the way to the left so it's over halfway. Now I'm going to enter 3 times. And it tells me -3 is my x-intercept. So I have one x-intercept I know is at -3, 0. Now I need to find the second one. I can't just move my cursor, watch. If I move my cursor, it's not staying on the graph. It's just moving on the line. But watch what happens if I hit second trace again. And number 5, it puts my cursor back to where I started. It always will. That's why you can't move your cursor unless you're in the second trace menu. Yes, sir?
I know.
Yes, deal with that. Yeah. Okay, so we're going to move our cursor over halfway. So it's over halfway, and now I'm going to enter 3 times. So now we find it's -2 and 0. And we're going to find the third one. Second trace 5, and now I got to move over halfway. There's my bottom hump. Excellent, I'm over halfway from the bottom hump. I hit enter 3 times. And there's my intersect as 1. So I have 3 x-intercepts in this case. Okay? My y-intercept is already in the equation. Let's take a look and analyze these questions. So, back up to where we were. Okay, so we've got all of our cubics drawn. We're going to talk about end behavior here. It tells us the description of the shape of the graph from left to right on the coordinate plane. That's what it's talking about end behavior. Which way do the tails point? Where do they start? Where do they end? Label the quadrants. So we've got quadrant 1, which is our problem-solving quadrant. Then we go left. It always goes left. 2, quadrant 3, quadrant 4. So cubic graphs, depending, will always start in quadrant 2 or 3. So if it is an up graph, that means x cubed is positive. If that is the case, it's going to start down in quadrant 3 and end in quadrant 1. Okay? If it's an up graph. So that's if x squared is positive, then it goes up. If x cubed is negative, it's going to go down. And if that's the case, you're now going to be going from 2 to 4. So it's different where they start and where they end, depending on whether they go up or down. Okay? Now, there's a few features about these cubics that we need to remember. One feature about a cubic is talking about the turning points on the top of the next page. Okay, so I'll let you get there. The turning points. This is when you will see hills and valleys. Okay, so your turning points are hills and valleys. There's always one less turning point than the degree. So a degree 3 for cubic, maximum times it can change directions is 1 less. So 1 less than 3 is 2. So the maximum times it can change directions is 2. Well, what about x squared? The degree is 2. Maximum times it can change directions is 1. Okay, it's always 1 less. And we will look at a few examples of that in a moment. So again, just to recap, if I've got an x squared, y equals negative x squared here in this case, negative because it's going down. So degree 2 has 1 turn point, maximum. It's always 1 less than the degree. So degree 2 can only change directions once. Degree 3 can only change directions twice. Degree 9 can only change directions 8 times. Okay, degree 100 could only change directions 99 times. Okay, it's always 1 less. And our degree determines the shape. So degree is the highest exponent on the x variable. Always the highest exponent on your x variable. That's what our degree is. So degree 3 would be a cubic. Degree 2 is our quadratics. Now we're going to analyze what we know about them. We're going to sketch some graphs. Okay, back to where we were. Constants in behavior is always going to be 2 to 1 because it's going to be in quadrant 2 and 1. Let's redraw that. That's crazy. So, here's our mini graph. It is going to be always 2 to 1 or 3 to 4, depending on if it's above or below the x-axis. It can only go left to right because it's a constant. There's no variable x. So this guy has no x variable. Okay? If he's got no x, he's a degree 0. You have to have an x to be a degree. He doesn't have an x, so no x, no degree. Domain and range. Well, your domain will be XCR, and your range is exactly equal to the number it touches on the y-axis. So it's y equals the y-intercept. Okay, so y equals the y-intercept. Does this green graph change directions at all? Nope. So if it doesn't change directions, it cannot have turning points. The y-intercept. The y-intercept is the number. So it's going to be y equals a number. It's going to be the number it tells you. Number of x-intercepts. Not applicable. It does not touch the x-axis at all. Okay? They will not touch the x-axis. Unless it's exactly on the x-axis. But remember, we don't deal with those ones. Linear graphs. Linear graphs, I'll just do a mini sketch here. We could have 2 kinds. We could have increasing or we could have decreasing. So, an increasing graph, so if it's going to go up, increasing is going to go from 3 to 1. Decreasing down is going to go 2 to 4. Always, always. Okay, so if you look at your graph right here, it'll show you which directions it's going. And just like we read a book, we start our graph on the left, which is why I've got the arrow on the right showing you the direction it's going. So, linear y equals x exponent 1. So, what is its degree? 1. Because that is the exponent on the x variable. It is identical here to there. It's the exponent on the x variable. Domain and range. XER, YER. Domain and range. All XER and YER mean is that there's no restrictions. Linear graphs have no restrictions on them. Number of turning points. Do they change directions? No, they're linear. They do not. The y-intercept. It is your constant. Okay, it's always the constant, the one without the variable. And the number of x-intercepts, it'll always have one x-intercept. It'll always have one x-intercept. Every graph we see will always have one y-intercept. Every graph does. But not every graph touches x. Okay, but every graph will touch y. Okay, let's take a look at quadratics. Quadratics, let me sketch you a graph. There are three types of quadratics. We have quadratics that never touch the x-axis, but they still change directions. So possible 0 x-intercepts, possible. We also have some that just touch it once and then change directions. So that would be 1 x-intercept. And then we can look and see others touch it twice. So we could have 2 x-intercepts. So just jumping over to the x-intercepts, the number of x-intercepts over here. It says the number of total possible. Well, we could have 0, 1, or 2. So the maximum is 2, identical to the degree, whatever the degree is. So, quadratic, y equals x squared. Because he has an x squared, we know that he has a degree 2. Those are identical. They match. So x squared means he's degree 2. The end behavior. If you look at my sketches that I've drawn here, there's only 2 possible end behaviors. If they're going up, they started way over here in 2, and they're going to end in 1. If they're going down, they start in 3 and end in 4. So we're going to have up is going 2 to 1, down 3 to 4. They can cross into other quadrants, but that's where they will start and that's where they will end. Now, if we look at domain and range, this one's going to have no boundaries on domain, but it's going to have a boundary on the max or min for the range. So, y is greater than or equal to the minimum, or y is less than or equal to the max. Okay, and that's the range. The range is a boundary, okay, because it changes directions, and it's a degree 2. Okay, so it's dependent on our minimum or our maximum. Number of turning points, always 1 less than the degree. This guy only changes direction once. And again, what's our y-intercept? The constant. Always, always the constant. Now we're going to go to our cubics. I'm just going to draw our little cubics down here. So we have cubics that don't change direction. We have cubics that'll change directions. No, that'd be a 4th. There, doesn't come down here. So we have it that changes twice. So we can have different kinds of x-intercepts. So we can have 1, 2, 3 x-intercepts. Whoa, where'd that one come from? Okay, I'm just going to clear all the ink. Has everybody got the stuff drawn for the top of the chart? Okay, I'm just going to clear the ink and so it's not so messy, and I'll move it down. Okay. Okay, so for our cubics. So, our sketch of our cubics, we've got some that don't change directions. We've got the ones that do. And some have x-intercepts, some don't. Okay? So, y equals x cubed is our cubic. It is a degree 3. They match. Okay, it's degree 3. The end behavior, if it's going up, is 3 to 1, down 2 to 4. Domain and range. Domain, no boundaries, XER. Range, no boundaries, YER. Then we're going to the number of turning points. It is 1 less than the degree. So we have a degree 3 It turns directions twice, maximum. Then we have the y-intercept. Again, it's going to be the constant. And the number of x-intercepts. You could have 1, 2, or 3 maximum. It is always equal to the degree. So it's a degree 3. It can touch x maximum 3 times. Okay? So I'm just going to show you real quick the 3 different kinds of cubics. So, as we know, 1 cubic does not change directions. Okay? Point of inflection. Then we've got the ones that'll touch x twice. So this guy touches twice. Then we've got the guys that touch it 3 times. So 1, 2, 3. So 3 kinds of cubics. Now, if we looked at our chart, hopefully you noticed something between degree 1 and degree 3. Look across on the chart for degree 1 and degree 3. Do you notice anything? Look at the end behavior and look at its domain and range.
Linear cubic is it goes like 3 to 1, 2 to 4, and then 2 to 4. Domain and range is x, ER, y, ER.
Good. Okay. So degree 1, 3, 5, etc. will have identical parameters, which means it will have the same domain and range. It'll have the same starting point and end point. So your your end behaviors. So degree 1 and 3, linear, cubic, we don't deal with anything above 3, but I'm just showing you if it's an odd degree. Okay, an odd degree, XER, YER. Okay, always. If they're going up, they're going to go from 3 to 1 going up. If they're going down, they're going to go from 2 to 4 going down. That is standard. That is always the same for degree 1, 3, 5. Okay? Degree 2 and 4 will always have boundaries on the range. Okay? So that's what they have in common, boundaries on their range. Okay? So, those are the major things we have to remember. These guys are going to have identical parameters, especially domain and range. We have to know those, XER, YER. Okay? Which means no restrictions. So if we read just below this, it's talking about the degree. And this is the basic definition of degree, where it says the degree of a polynomial is the greatest power of the variable x. So whatever your largest exponent on x is, that's your degree. If I have y equals x exponent 7, I have a degree 7. Okay? Okay, this is our basic definition of a polynomial. So far we've been dealing with polynomials and talking about their degree, but literally what is a polynomial? It's any algebraic term that is separated by positive and negative signs. So any expression where you've got terms separated by positives and negatives, that's a polynomial. So we're going to go down, we're going to find out what the Hebels we have for leading coefficient, degree, and constant. Now don't be afraid of the way it looks. We're used to seeing our equations as y equals, or the equations equaling 0. All they've done is they have changed the y to something for problem solving. That's all they've done. This is called function notation. And they use function notation for problem solving. That's what it's for. So this one might be talking h for height. The next one, k for kinetic energy maybe, or kilojoules or kilograms. F could be a function. G could be grams or greater. Who knows? Okay. So we're going to talk about leading coefficients. The leading coefficient is always the digit in front of your x with the largest exponent. So here, when it's in a fraction, this is the same thing, because there's a hidden 1, as me saying 1 over 8 x. You have to remember that. If there's a variable and then a number, they're actually attached. That there's a hidden 1 in front of that x. The x will always slide to the top number. So it's actually 1x over 8. So the coefficient here is 1 over 8. Okay? The degree is your highest exponent on your variable. And in this case, we have a hiding 1 on our variable, so it is a 1. Do we have a constant? No, not applicable in this case. We do not have one. The next one, leading coefficient. We have an x to the 5. So we need to look and see what number's in front of x to the 5, because x to the 5 is our largest exponent on our variable. So we've got a -2 in front. That's our leading coefficient. It's always in front of the variable with the highest exponent. Degree, it's the highest exponent, so it will be 5. Do we have a constant in this case? 4. Perfect. The next one, we're looking for our variables. I've got a degree 1 there. Oh, and I got a 4 here. Who's bigger? 4. So I have degree 4. So now I'm going to look in front of that 4, or that x to the 4, and see what I've got here. I've got a -4. So my -4 is my leading coefficient. Do I have a constant? +3. Good. The next one. Don't forget, there's a hidden 1 in front of that x. So that's actually 1 over 5 in front of x to the 3. And again, highest exponent is a 3. It's a cubic, degree 3. Do I have a constant? -7. There's another one I want you to write down. We're going to have 2 over 3 bracket 6x squared minus 4x plus 2. In this case, triple hint, triple hint, you're going to have a question like this on your exam and on quizzes and assignments coming up. If it wants your leading coefficient, right now, it looks like it's the 6, but you need to remove the brackets to prove it. So what you've actually got to do is you've got to multiply the 2 over 3 into the bracket. When you do that, in your calculator, you're going to put 2 over 3 in brackets, and you're going to times it by 6, and then you're going to math bracket, and it's going to give you a 4. That's going to equal 4. So our leading coefficient is actually 4, not 6. Okay, so this guy, our leading coefficient would be a 4. It's a degree 2 because I have an x squared. And I have a constant, but is my constant +2? No, because I have to multiply this guy in. So 2, it's always multiply by the top, divide by the bottom. So 2 times 2 is 4, divided by 3 gives you a decimal, so we're going to leave it as a fraction. 4 over 3. So it'll be 1.3 repeating. Okay? So if there's a coefficient out front of a bracket, you've got to multiply it in to find everything. In order to analyze it, you need to multiply that coefficient in. You will see questions like this. Okay? All right. These are the basic characteristics on the chart below that you see. I want you to read that over real quick for a few minutes, and we're just going to pause here for a moment. Push play when you're ready.